Let's get right into it. Welcome to this explainer. Today, we're doing something a bit different, a really focused structural exploration into the hidden resource networks that actually make AI reliable. We're going to look at how an AI's reliability isn't just about raw intellect or parameter count. It's fundamentally about how information is routed, verified, and released when resources are, strictly limited.
So let's kick things off with a massive question. Why do these highly capable, meticulously trained AI models still confidently pump out, fluent falsehoods? Usually we brush off these hallucinations as just isolated bugs or factual glitches, but what if we flip the script? Ask yourself, how on earth does any system stay stable when the sheer mountain of information it's generating completely outpaces its ability to actually verify that information?
There's a fascinating perspective from a recent theoretical paper that hits the nail on the head. It argues that a lot of these failures are actually reliability failures induced by local training and evaluation incentives. That's a total game changer for how we view this. It means hallucinations aren't just random mistakes or weird defects. They're cutting corners because they're totally overwhelmed and structurally incentivized to just keep talking. Basically, they're doing exactly what we've evaluated them to do.
Okay, here's our roadmap for the explainer. First, redefining AI hallucinations. Second, the trap of local rewards. Third, the energetic paradigm framework. Fourth, 4 paths of response routing. Fifth, optimizing global path efficiency. And finally, implications for AI governance.
Let's start with Section 1, redefining AI hallucinations, moving beyond generation errors. To really grasp why models confidently invent facts, we've got to stop thinking of hallucination as just a generation error. It's usually a symptom of a structural bottleneck. Think of it like a slammed hospital ER, right? If 100 patients rush in at once and the triage nurse has to diagnose everyone instantly without running any tests, mistakes are absolutely inevitable. AI systems hit this exact same wall. A systemic failure kicks in when too many claims flood the verification pipelines. Review capacity is tightly capped, and we aren't prioritizing the high-consequence stuff. When generation completely overruns checking capacity, the system is basically forced to spit out uncalibrated guesses.
Moving right along to Section 2, the trap of local rewards and why models always answer.
So if bottlenecks are the root cause, why do models just plow right through them? Well, this comparison brilliantly illustrates the core conflict. On one side, we have local reward maximization. This evaluates the model step by step, basically handing out points immediately just for producing an answer. Over on the other side, we have global path efficiency. This actually internalizes the downstream burden of correcting an error. And this matters immensely. Right now, we're practically handing the AI a cookie for giving us an answer right this second, rather than rewarding it for taking a breath to ensure that answer won't cause a massive headache down the line.
Which brings us to Section 3, the energetic paradigm framework, our new structural map. To escape this local reward trap, we desperately need a new way to measure stability. Enter the energetic paradigm. In this framework, the claims an AI makes are treated as units of informational activity, and the resources needed to verify them, those act as strictly limited, almost physical, energetic resources. Because of this, the routing decisions, how the model actually directs a query, literally determine the stability of the entire system. Building reliable intelligence means we have to manage these flows, not just blindly crank up generation power.
Now, the really cool part is that we can mathematically measure these constraints the exact second a query hits the model, using 4 latent state variables. First up, internal answer sufficiency. Does the model actually know the answer? Second, evidence completeness. Did the prompt give enough context? Third, ex ante verification. How easy will it be to spot a mistake? And check out R at the bottom, the consequence-weighted reliability cost. Look, an AI writing a cute poem has a super low consequence cost. An AI diagnosing a rare disease, massive cost. The system absolutely has to know the difference.
Okay, Section 4. 4 paths of response routing, the claim queue architecture.
By putting those 4 variables to work, we basically upgrade the AI from a naive answer generator into a highly sophisticated routing module. Check out these 4 lanes. Lane 1 is answer. Generate a response directly when internal sufficiency is high. Lane 2 is retrieve. Pause and gather external evidence because the path is incomplete. Lane 3 is abstain. Defer the answer when things are unresolved but the stakes are low. And Lane 4 is escalate. Kick the query over to qualified human review because those consequence-weighted reliability costs are simply too high to risk messing up.
If you glance at the mathematical trade-offs for these actions, it becomes super clear why routing is the whole ballgame. Sure, a direct answer might look cheap right now, low immediate cost. But if it's wrong, the downstream correction costs are astronomical. Choosing to abstain or retrieve actually preserves the system's global energetic efficiency because it dodges that massive hallucination penalty later. For us users, this translates to an AI that's finally smart enough to say, hey, I need to look this up, or just, I don't know, saving us from acting on a very costly hallucination.
Moving to Section 5, optimizing global path efficiency, shrinking the answer region.
So what happens when we actually enforce this structural routing logic? Notice how the model's behavior dynamically shifts based on the stakes. Bar 1 shows the threshold for directly answering when the consequences are a drop in the bucket. But look at Bar 2. That risk-adjusted threshold for direct answering severely contracts when errors become harder to catch or the institutional stakes shoot up. The model is forced to demand a significantly higher internal certainty before it simply hits answer.
And you know what? This elegantly explains a huge empirical puzzle we see in AI development. Sometimes, as you scale up a model, its hallucination rate suddenly plummets, just drops right off a cliff. It's a lot like boiling water, right? The temperature goes up smoothly, but that transition from liquid to gas, boom, happens all at once when a threshold is hit. AI capabilities do the exact same thing. The underlying capabilities grow smoothly, but once that smooth growth crosses the strict mathematical routing threshold we just looked at, the observable behavior snaps. The model suddenly starts reliably routing to answer instead of abstain.
Finally, Section 6, implications for AI governance, moving from post hoc to upstream. Adopting this energetic paradigm makes our next steps crystal clear. First and foremost, we have to shift our safety interventions upstream right into the routing action space, instead of always relying on messy, after-the-fact fact-checking. We've also got to stop penalizing models on benchmarks when they smartly and safely abstain. Training data labels need to be heavily conditioned on verifiability and consequence class. Ultimately, basic calibration, knowing what you don't know, is just step one. That calibration has to systematically inform the routing decisions, not replace them.
So as we build these wildly complex systems, we really have to stop and ask ourselves, are we actually evaluating AI on its reliable intelligence, or are our current metrics merely testing its willingness to confidently spit out unverified claims under pressure? By shifting our focus to exactly how information is routed, verified, and released under strictly limited resources, we can finally begin to engineer the true energy structure of reliable AI. Thanks so much for joining me for this explainer.